Good morning. I'm Josh Kent. I work with Cliff at the Center for Geoinformatics. I do the research in GIS and most analysis. As Cliff was saying, the geoid and particularly gravity is useful for measuring subsidence. I'm going to show you other utilities that we use to measure subsidence in Louisiana, particularly related to a paper that was just recently published. We collaborated with some researchers and scientists from the Jet Propulsion Laboratory at Caltech. These guys are the satellite and really radar instrument experts, and you're going to see some of the examples of that. But they came to us because we had the Corps' network. We had continuous GPS reference stations in their study area that provided them the ground control to make the measurements that you're about to see. So here's a presentation overview. We're going to look at subsidence a little bit, how we utilize the Corps in that process, and some findings. And if time permits, I can show you a few more details of each one of these methods. I like this photograph of the cruise ship that appears to be above this streetcar. There's no photoshopping here. It was just a unique angle, but it's really impressive about how Louisiana's kind of precarious situation. This is in New Orleans East, and this is pretty typical for some of the more heavily subsiding areas and indeed places that get actually uplifted for flood control. But the general processes of subsidence in Louisiana, it's sensitive, wow. All right, general processes include sediment compaction and consolidation. This is stuff you might see in the shallow range, but you can actually take it further down. You have loading of the lithosphere. The actual Earth's crust is bending under the mass and the weight of the sediments and the water that's on top of it. But there's also an anthropogenic component, which is probably the most significant driver in New Orleans area. And that's related essentially with water. As we drain the soils and they desiccate, they become dry and they compact and consolidate much faster. And we also have groundwater withdrawal. And this is very basic general overview. It gets much more in depth. But the interesting things are that we actually can drive the subsidence in our own location, and we may not even realize it, mostly because we don't see it. It's not visual to us. Back in 2006, some scientists, including one of our former director, Roy Daca, published this. It's using satellite-based radar from an instrument called RadarSat. It's a Canadian spacecraft, to look at subsidence rates in the greater New Orleans area over a period of time. It was actually a handful of years. You may not be able to tell in this graphic, but each one of these little color changes are really pixels from that instrument, and it's showing how much the surface has deformed over a period of time. So the redder the pixel, the more deformation has occurred. Because it's in the greater New Orleans area, much of this is actually just reflected off of hard surfaces, but there are confounding variables, including vegetation that grows a lot and water levels that change. And this continues to be a problem with this kind of technology, which is a radar technology, synthetic aperture radar. But as you'll see, improvements have allowed us to look at things in much more detail than ever before. Including this publication that actually just was released this summer. And it looked at, it used, instead of a satellite, it used an aircraft to fly over the greater New Orleans area. It was maintained by NASA. And it was between, I think it's June 2009 and July 2012. And it wanted to measure the amount of deformation that's occurred over that period of time. That's the aircraft itself. It's an L-band radar instrument if you're into that kind of thing. But pretty much as it flies over, it's taking an image or an active image of the surface. Whatever bounces back is recorded, and then they go home. It's not until they come back later that they make the instrument actually fly the aircraft in exactly the same position it was at the first time, at the first look. And it fires its radar, and the return that comes back is then compared to the first to measure the difference. And that's what you're about to see. So yeah, these screens are kind of small, but if anybody's interested in the paper, I'm happy to email it to you. But what you see now is a higher resolution from the satellite instrument of what the subsidence rates are in New Orleans, and you get this sort of iridescence kind of change in color across the surface. And what this is showing you is essentially the phase difference in the topography, how much the instrument measured deformation. The redder and oranger that difference is, the more substantial. In this case, up to 35 millimeters per year. If you look around the Crescent City area, you see it's mostly in the purples, some blues. It's not too significant, but there are some hot spots here and there. The most significant area is actually in New Orleans East by Michoud. This is just an image to show you sort of the confidence that we have in the results. Of course, anytime you see a scientific article, if you don't have a confidence, you should just move on. It's not going to help you. So while we did see extremely high rates of subsidence in the east, you'll see that the red confidence is not so great in the east, and it means that we have to pay more attention to it. Fortunately, we had a core site. We still do maintain 2 core sites in the area that we can validate the results that we identified. So just as sort of a proof of concept of what this instrument could detect, we were looking at essentially any surface that's going to reflect that radar back really well without any confounding variables like growing shrubs and grass, which can actually mess up the radar. So in this case, we looked at residential areas, and we found that there was a high correlation of subsidence in newly developed neighborhoods. Neighborhoods that came up in 2009 had the higher rates of subsidence than neighborhoods that were long established, suggesting that there's a compaction going on for short-term construction that is detectable by this instrument. There is another situation that was kind of interesting. It turns out there was either a renovation or just a complete collapse of a roof. In the very center of this picture, you might be able to make out a hot spot surrounding what looks to be some sort of warehouse, maybe a grocery store. If we zoom in or focus our attention on that area, you can really see that there was a massive change in the height of that rooftop associated with some kind of construction. So the good news is that the instrument was actually telling us something that isn't just noise. It was distinctive because of the surfaces that are reflecting the data. We looked at a few places in particular, the greater New Orleans area and then east along the essentially industrial corridor of the Mississippi River. And particularly Destrehan and Lakewood Elementary are core sites that we have there. And these are actually precise point positioning plots, time series of the position at these core sites in east, in north, and vertical. And you can see for Destrehan, it's subsiding at 2.11 millimeters per year, plus or minus 0.3. And then for, actually it's not Lakewood, it's Lutcher. Lutcher is subsiding at 1.285 millimeters per year, which is kind of slow for the area, suggesting that maybe because it's on a natural levee, that's not subsiding as much as we might expect. But of particular interest was right by the Bonnet Carre, and you can see that here's some I gave this presentation actually in Europe, so I had to make sure people understood what was going on. But what you see here are 2 power plants. You have the petroleum refinery at TaFT, you have Norco, and then of course the Bonnet Carre. And when you look at what's going on here, you can see some pretty shocking results. I gave this presentation also at an engineering conference and got some really fascinating feedback from some people who have actually worked in the area about what might be driving the subsidence here, and it's not what we expected. But looking particularly at the Bonnet Carre, you can't really make it out too clearly here, but there's a line of red on the flooding side of the spillway. And it turns out it's probably that water that collects. I wonder if here we go. I don't know if you can see my cursor, but this is water inside this concrete structure. And then when the water evaporates or drains away after a period of no rain, you can actually detect measurable changes in surface elevation. So that was kind of interesting. Some of my co-authors were convinced this whole thing is subsiding away, and it's like, I don't think so. That would be unusual, but it certainly would have gotten noticed. But it's fascinating to see that the instrument is capable of detecting something as small of a surface area as water inside that channel. Perhaps more interesting is what's going on the other side of the river at TaFT. So here we have, it's a conglomeration of various refining and chemical processing and manufacturing, and it's clearly a hot spot right underneath the letters TaFT. So what might that be going on there? So the original thought process is groundwater withdrawal. There are a number of deep wells in this area that have been used in the past to extract water, but according to all of the reports, none of the manufacturing here is extracting any fluids from the ground. So what might it be? Either A, they're lying, which is possible but unlikely. But as it turns out, from a guy who actually used to work in the area, he suggested it might be vibrations. That there's so much activity inside of these plants and inside of these manufacturing that you could actually get a vibrating subsidence on the surface that might indicate this rate of deformation that we see here. That would be really fascinating to explore in more details, and it's something we're definitely going to do. But this is what the region looks like. It's actually broken up by a number of different businesses doing various activities. But if we focus on New Orleans East, this has been an area of interest at LSU for some time, mostly because of the Michoud Fault. It's a strand of the Baton Rouge-Tempétate Fault that runs north from Baton Rouge across over the Lake Pontchartrain, and it's believed that essentially a finger of this fault is going south and directly underneath Lake Pontchartrain towards New Orleans East. And it would be a very deep fault since it hasn't really, there's no surface expression at all. So the question is, could it be that some kind of activity in the region is factoring in as possibly causing that fault to slip? Well, the area used to have NOPSI power generation there, in which they extracted enormous quantities of water. Now Entergy runs the site. They don't extract nearly as much deep aquifer water as they once did, but you definitely see hotspots of subsidence where you would at least correlate with water extraction. Now I mentioned earlier we have some core sites there. We actually have two, and because we know who butters our bread, we named them Moon and Mary Landrew. We might be installing a Mitch sometime soon if we can figure that out. But Moon and Mary are a science project. In the foreground on that blue casing is Mary. That casing is 2,000 meters deep. And the idea is that you really can measure subsidence with our core sites based on the bottom of the foundation of an instrument. So in this case, if you look at the antenna and go straight down, you're measuring subsidence at the bottom of that casing, 2,000 meters down, which is where we believe that fault might be. Moon is in the background. It's actually sitting on a concrete pedestal that is only 17 inches into the surface. So in effect, we're looking at two different rates of subsidence, one that is deep and one that is shallow. And they're right next to each other, about 10 feet apart, so it's great. We can make these one-to-one comparisons. I can show you some of that in a little while, but for right now, you can see that as of a few weeks ago, Mary was subsiding at about 2.37 millimeters per year. Now what's interesting that I'll show later if time permits is that Moon is subsiding not much slower than that, which is a bit of, or faster than that I should say. It's about 3.1. So the question is, why does Mary represent more subsidence, or the majority of subsidence, that Moon is observing? And Moon is shallow, so it should be subsiding much faster, but it's not that much faster. So what could it be? There's a lot of hypotheses that we've been throwing around. It's possible that, well, one, we definitely do not know what's in that casing because it's been sealed off since the end of World War II. It was sealed off with 1,900 bags of cement, according to the report. So it could be that maybe the mass of all that cement is pushing it down. It could be that the Holocene that is surrounding that casing is actually pulling it down, kind of like an anchor, causing it to subside at a rate that's faster than we anticipate. There might be even differential rates of subsidence along the entire 2,000 meters of casing. Whole bunch of questions, very few answers, but that's what science is all about. Well, when we go back to looking at strictly these radar data and the subsidence observed at the radar data, we definitely see some really fascinating phenomena going on, and it was verifiable with the 2006 publication of essentially the same area. And we see pretty much that, if anything, the region is subsiding faster than it did in 2006. And of course, you can also see unique features that are reflecting that radar signal back, particularly flood control structures and roadways that are subsiding. This is where Entergy is now, and that's the green bridge going across, I believe. So you can definitely see what's happening right here in New Orleans East, Michoud area. All right, so the summary is that this radar technology, which we cumulatively call INSAR, Interferometric Synthetic Aperture Radar, is really going to be the next big thing for subsidence monitoring, because it's not just discrete points that have been used in the past where we look at just GPS, but we can actually see a surface. Yes, sir?
Several years ago, we had talked to USGS out of California about using the INSAR data going back to the 90s. At the time, there were only two algorithms, public one, which wasn't given real great resolution, and the Italian algorithm, which was proprietary. And at the time, they were having to have a surface area to create a synthetic antenna of a certain size. What's the status now? Are there revised algorithms and the size of these antennae that have they been reduced?
For airborne INSAR techniques, the antenna is, I could go back to the picture. It's essentially a pod that you can attach underneath the aircraft, and it's a side-looking radar. You have a long track and an azimuth that you have to measure. The algorithms themselves have obviously improved with technology. I wasn't aware of any proprietary algorithms apart from maybe those developed by private companies. In terms of the scientific community, there are quite a few that are utilized directly. Most of them are just mathematical formulas that people program themselves in some kind of open source framework. The majority of the analysis that I've used recently are all open source. They are GNU licensed, so and they all are customized. The different algorithms are customized for the different instruments. So you have the airborne instruments, you have satellite-based instruments, and you have different polarity or polarization that you're measuring, whether it's vertical or horizontal, and the mix quadruple. So all of that is available in open source at the moment. I don't know if I directly answered your question, but it's improved.
But I remember the guy, when we were looking at it, he was saying you had to have a certain effective area of a certain size, let's say 30 feet by 30 feet. Have y'all reduced
Oh, no, it's much smaller now. This particular instrument, it's actually in the very beginning, but it's measuring about a 6-meter pixel spacing. Typically, but this is assuming that you have coherence between the two observations. Coherence just means that you're actually getting a good signal from the first look compared to the second look and vice versa. Sometimes you just get poor coherence where they're not lining up exactly right because of essentially the instrument, the aircraft itself is not in exactly the same position it was when it took the first picture. So if we can line them up really well and get solid coherence, we're looking at 6-meter pixel spacing. For the satellite stuff that's out there now, particularly the Sentinel-1 and 2 system that the European Space Agency are managing, we're getting about 20-meter pixels, and that's from orbit. So lower resolution on the surface, but it's pretty good. It's not the 30 meters that it used to be. In fact, you can get probably about 12 to 15 if you have really good coherence.
And you can go back to the 90s with that data, right?
Yeah, some of the data, because some of the time series and some of the instruments themselves have been operating since the 90s and the same framework, like RadarSat particularly. Yeah, you can look back at that, along with some other instruments that are out there.
So you actually are getting the raw data, and you have your own algorithm that you're manipulating,
The JPL people have their own algorithm. They're using a handful of different toolboxes. This is getting kind of esoteric. I'm happy to talk to you about it offline.
You're saying that's the way it's going. So
yeah, that's the way it's going. Yeah, yeah, it is. It's still not for the faint of heart.
Trying to get regional subsidence across the whole state for planning purposes. Sounds like
it is a great tool for that. The variables that still need to be resolved are vegetation growth, and particularly in the South, Louisiana, where we have rapid growing vegetation. You know, 6 weeks you have different surface heights, you know, from a reflective point of view. So we have to find ways to constrain that, particularly using masking techniques. The higher resolution survey information you have, the better you can mask out those confounding variables like vegetation, like variable water levels, which happens a lot, particularly after it rains. Radar is absorbed by water. It's just you can't see it unless it can penetrate into some, you know, dirt and material in that water itself. So when we have a heavy rain, all of a sudden now some of your surface is just completely unusable. We'll have to, you know, address those issues. But
if you have parking lots
yes,
and bridges and other features that are there for years and years, you can get some pretty good regional
you can get
stuff.
some really good regional stuff, yes.
Yeah.
And they have reflectors that you can build. They're maybe the size of these tables about, they're kind of pyramid shaped. You can put these into wetlands at particular locations to monitor vertical change and deformation patterns in wetlands. But you're going to have to tolerate the fact that you have this large pyramid looking thing in the middle of a field that I'm sure hunters are not going to like. But birds will.
How did you get the accuracy estimates you mentioned on one of your slides of the accuracy?
For the confidence level?
Yeah.
So it's essentially based off of coherence, how often the pixels stay coherent. We had a threshold level of essentially from 0 to 1. We set a threshold of 0.6. So we only looked at pixels that had 60% coherence between observations. Just recently, in fact, the Sentinel satellite system, it's actually collecting data for Louisiana because of the request from our partners at JPL, but has also been collecting data, obviously with a lot of interest in the West Coast, where there's an enormous amount of plate tectonics. INSAR is very valuable for measuring deformation as a result of earthquakes. Well, they also happen to capture some buildings in San Francisco, and one building in particular is leaning, and they're calling it the Leaning Tower of San Francisco. It's actually subsiding in a bad way. It's going to be interesting to see what they're going to do about this. But they were able to measure with some confidence the amount of subsidence occurring on that actual structure. This INSAR technology is going to be pretty big, and it's going to provide not just discrete observations, but observations for continuous areas. something that we have not really had in quite a long time without leveling. Yes, sir?
I have a question. Could you go back to the very beginning slide?
Yeah.
So, I guess what I was looking to see there, I remember you saying that there was much subsidence taking place over on that concrete slab that might have been anticipated.
Actually, I might have a better picture. Let me go to it. There we go. So that's a different angle, but you can see now Moon is in the foreground, Mary is in the background, and you can see our antennas attached to each of those.
Right. What I was looking to see if there was some type of influence that each wall facing was exerting on either the slab or the surrounding ground.
It's actually isolated. It's
See,
not,
it's isolated in the slab.
yeah. This is grass growing in a square around that slab.
But I guess you feel it's too far away from the casing for the casing to be holding up the ground due to shear forces and the drag.
Well, I can't eliminate it, but it is as constrained as it's going to get, obviously. I'll show you something else that's interesting.
But I guess the question about that is that casing for the merit depot, it's not sleeved, right?
It's sleeved.
It is sleeved.
Yeah.
So it's actually anchored only at the bottom and it's squeezed and moved all the way to the top?
Presumably.
But I thought it was grouted in.
Oh, it is grouted in, and I guess it's capped, and we're attached to the cap.
So it's a casing inside of another casing?
Probably, yeah. We don't know. They actually, that's the one well that does not have any information. So it's got to be bad.
Not a grease leak. That's a wastewater well. That Mary set on top of.
We don't know. It's a waste well. It's an injection waste well. Yeah, right. Yeah, and Larry, the field guy, we were able to get actually data from NASA about the sites, and there's a database on the Sunrise website for all wells that tells you exactly what's in the well, but not that one. Yes, sir.
The NGS used to have a benchmark.
It's still there.
Same place?
Same place.
Well, as Mary?
Yes.
Okay.
Isn't there a core station there also?
Yeah, that's the Mary core site. Yeah.
Does NASA not have any historical construction information on that?
They do, and they said it was used during probably when they were building the Higgins boats there during World War II, and it was a waste injection well.
But as far as how it was constructed,
Nothing, other than it's 2,000 meters deep. And it's filled with cement.
and it's in the it's south of the fault line.
Presumably, yes. And so this is where it gets interesting. So this is the Moon subsidence rate, and you can see it's subsiding about 3.046. Mary was 2.8, so not that much more on the surface. And so it's not what we expected. I'm going to go through these kind of. Let me get out of this. Where is it? I messed it up. What I was going to show you is the really fascinating thing is that they're going in different directions, which is even more interesting. This is where the notion of an anchor came in. Okay, so if just a brief geology class, right? We have Holocene, the youngest material on the surface, and the deeper you go, the older the material, the older the sediment process. Mary goes all the way through the Miocene, right? So you have Holocene, Pleistocene, Pliocene, Miocene. What if the Holocene and all of the younger material is moving at one rate, but the stuff at the bottom is moving at another rate, you could essentially get a tug. And we were wondering if maybe it's tugging, because it is actually moving to the south and west, whereas Moon is moving to the north and east. Fascinating. It's just absolutely fascinating. So, let's see. I'm going to try to get... All right, here we go. Where's my cursor? All right. So yeah, these arrows are not very clear. I'm showing two different reference frames here. I'm showing an IGS, the International GNSS Service reference frame in blue, and these are vectors. And what that means is that all of these core sites are referenced relative to a rotating globe. It's the Earth as a whole. The red vector arrows are actually constrained to the North American plate, so they're going in a different direction. And particularly of interest is Moon and Mary right here. Moon is moving, so there it is, Moon is moving to the northwest, Mary is moving to the southwest. Science. Some of them are moving to the southwest also. So, and those tend to be close to levees. If you notice, they're the ones that are a natural levee system, except for maybe Destrehan, which is also like on a northern levee, but it's moving to the northeast. So it's really just interesting to see these different vectors show up in the data. I've taken up way too much time. I apologize, but I thought you guys might be interested in seeing how we use our core sites in combination with the latest technology to measure all this surface subsidence. Questions? If you think of any after, I'm happy to chat with you about any details.